Hello everyone, today we are going to study the instruction set of 8086/8088 microprocessor. Earlier in a topic on how 8088 works, the functioning and working mechanism of 8088 microprocessor was discussed. The instruction set of 8086 and 8088 both are similar is discussed in this text. The 8086 microprocessor is a single chip central processing unit. CPU in short is a short form of central processing unit, was designed by Intel Corporation in the 80s. The microprocessor is one of the oldest one. For better understanding the Intel architecture from the software perspective, it is still taught in many Indian and foreign universities. In other ways, if one is conceptually clear about the 8086/8088 microprocessor, it is not very difficult to understand the architecture of microprocessor used in a modern desktop like Pentium or any other microprocessor. Further, the purpose and the objective of today's topic is to understand the various instructions of 8086 instruction set, which helps the assembly language programmer to develop programs on the microprocessor. Also, it gives the clarity to the viewer understand the operation of the microprocessor system from the software point of view. That means, we need not know the function of signals at various pins, their electrical connections or other hardware details. Rather, the important aspect of the study is that how the instructions of the 8086/8088 work using various registers. The details of the various registers also were explained in an earlier topic on how 8088 microprocessor works. So, we start with the instruction set of 8086 microprocessor. The instruction set of a microprocessor defines the basic operations that a programmer can use and design programs using these instructions. The 8086 microprocessor provides powerful instruction set containing 117 basic instructions. The basic instructions has a wide range of operands and addressing modes available, so that the basic instruction expands into many more instructions executable at a machine level. For example, the basic move instruction has 28 variants in the form of 28 different move operations, with each move operation supporting operands and addressing modes. We divide the instruction set of 8086 in 5 different categories. The first category is data transfer instructions. The second category is arithmetic instructions. The third category is logic instructions. The fourth category of 8086 microprocessor instruction set is shift instructions. The fifth category is rotate instruction. The first group of instructions, called data transfer instructions, is used for transferring data from one internal register to another, or provides data transfer between internal registers and the memory locations. The group further divides the data transfer instructions in 6 categories, like first is move, second is exchange, third is translate, called accelerate in short, fourth is LEA, which is load effective address, fifth is load data source, and sixth is LES. The instruction move is used to transfer a byte or word between register to register or register to accumulator or register to memory location pair. The table below shows the valid source and destination operand variations. The important thing to note about the move instruction is that the data cannot be transferred directly between two memory locations designated as source and destination. The reason is that the address mechanism required to address source and destination may occupy more bytes, increasing the size of the instruction. Instead, the move instructions are available to transfer the data from memory to internal registers and move them to the desired memory location. So, a single memory operation is dealt with the help of two move instructions. The instruction, for example, move AL, BL performs the data transfer from the contents of the register BL to the register AL. Since the operands are 8 bits, the move operation is called 8-bit data transfer operation. The instruction move DX, CX performs a 16-bit data transfer and transfers the contents of register code segment, which is 16 bit, to another register DX, which is also 16 bits. So, it is called a 16-bit data transfer operation. The another category of move instruction is register memory operation. In all memory reference move instruction, the effective address of the memory location is computed as the offset specified in the instruction, added with the contents of data segment register, which is shifted left by 4 bits to make it a 20-bit register. Take example of, say, instruction is move sum, AX. In this instruction, the memory location identified by the variable sum is specified using direct addressing. Let us assume that the contents of the data segment register is equal to 200 hexadecimal and the sum corresponds to the displacement of 1212 hex. Then the physical address of sum will be computed as 0200 with 0 appended, that means it becomes a 2000 hex, plus 1212 is added, that makes the address as 3212 hexadecimal is computed. The contents of memory location 3212 H are then used to store the contents of AL. The contents of AH, which is the higher 8 bits of the register AX, are then stored in the next memory location 3213 hex. Thus, the effect of the instruction can be explained as AL is transferred to the memory location 3212, AH is transferred to the memory location 3213, which is the next memory location after 3212. The next category of move is exchange instruction. In a exchange instruction, the short form of exchange is XCHG. The contents of the specified operand pairs are interchanged, and an exchange operation can be performed between a pair of operands using multiple move instructions. However, certain application requires this task to be performed efficiently. The exchange instruction called XCHG in short performs the exchange between a pair of operands. The operands could be register to register or memory to register or accumulator to register. For example, exchange AX, BS performs the exchange operation if the contents of the register before the execution of the instruction were 1212H and 3434H respectively. After the execution of the exchange instruction, the contents of the AX and BX respectively will be 3434 hex and 1212 hex. The next category of the data transfer instruction is accelerate instruction. The accelerate instruction has been provided in 8086, 8088 instruction set to simplify the implementation of lookup table operation. When using accelerate, the contents of the register BX represent the offset of the starting address of the lookup table from the beginning of the current data segment. The 8-bit register AL represent the offset of the element to be accessed from the beginning of the lookup table. The 8-bit address specified in the AL restricts the size of the lookup table to 256 bytes only. The value in both BX and AL must be appropriately initialized before the execution of accelerate instruction. The accelerate, when it is executed, replaces the contents of AL by the contents of the memory location specified by the following address computation as explained earlier. Again 4 bits are appended to the data segment register, making it a 20-bit address. This 20-bit address is then added to the register 16-bit BX, followed by addition of AL. The contents of that memory location are replaced in the AL. The example of use of this instruction is in software code conversion from ASCII to FDIC or FDIC format to ASCII format. The storage format of characters in desktop or Unix computer system is in ASCII format. However, the storage format on the IBM mainframe is in FDIC format. A file stored in the ASCII format must first be converted into FDIC format before being used in a mainframe system. To achieve the data transfer, a table of FDIC characters is stored in the memory. The individual FDIC codes are located in the table at element displacement equal to their equivalent ASCII character values. That means, the FDIC code C1H for letter A would be stored at displacement 41H, which equals the ASCII character of character A from the start of the table. The accelerate instruction converts the value stored in AL into its corresponding entry in the lookup table. Using accelerate, thus a character stored in the ASCII format may be converted to FDIC format. Another data transfer instruction is load effective address, that is called LEA in short, is used as LEA SI, which stands for source index register, comma input. When this instruction is executed, it loads the SI register with an offset address value derived from the label input. The value of the offset is represented by the value input as shown in the instruction. The other two instructions, LDS and LES, are similar to LEA except that they load the specified register as well as the DS or ES segment register. For example, consider the instruction LDS SI in brackets 200. The execution of the instruction loads the SI register from the word location in the memory whose offset address with respect to the current data segment is 200 hex. If the contents of the data segment register are 1200 hex, then the physical address will be computed as 1200, again 0 will be appended, making it 12,000 hex, and this will be added to the input which is designated as the 200 address. Overall, when 2 are added, the effective address is 12,200 hex. The contents of the 12,200 hex will be transferred to lower bits of SI register, and the contents of memory location 12,201 hex will be transferred to upper bits of SI register. So, this is how the instruction LDS works. Next, we talk about the arithmetic instructions of 8086/8088 microprocessor. These instructions are used to perform arithmetic operations like addition, subtraction, multiplication and division operations. These operations are available on operands in which the numbers are stored in a variety of different data formats. The data format can be unsigned or signed binary numbers, BCD format, or the number represented as the sequence of characters in ASCII format. In BCD format, the 2 digits are packed in 1 byte, whereas in ASCII format, 1 digit is stored in 1 byte in its ASCII code. The result of an arithmetic operation is generally stored in the accumulator register. However, it also affects the status flags. That means, the execution of an arithmetic operation affects the status flags. The flags that are affected by the arithmetic instructions are carry flag called CF in short, auxiliary flag called AF in short, sign flag called SF in short, 0 flag called ZF in short, parity flag which is PF in short, and the overflow flag which is OF in short. There are 5 different addition instructions. The first add instruction has a format add d comma s, which performs the operation s plus d. That means, it adds the destination and the source and stores the result in d. The D is either a 16-bit accumulator register called AX or an 8-bit accumulator register called AL. This AL, which is 8-bit accumulator register, is a part of the bigger 16-bit AX register. Both the arithmetic operation, whether 8-bit operation or 16-bit operation, affect the status flags. The carry flag, which is called CF in short, is set to 1 if carry is generated out of the result. The auxiliary flag is set to 1 if the carry is generated from 4th bit to 5th bit in case of an 8-bit addition and 8th bit to 9th bit in case of a 16-bit addition operation. The most significant bit of the result is copied into a sign bit, and therefore, the sign flag is affected as per the status of the most significant bit. The 0 flag is set to 1 if the result of the addition operation is 0. The S in the instruction add D, S could be one of the data registers or a constant number specified along with the instruction. A variant of the add instruction is ADC D, S, which performs S plus D plus carry operation. That means, along with the 2 operands specified in the add, the carry is also added into the result, and accordingly the result of S plus D plus CY flags are affected. In short, the addition of the 2 numbers is added to the carry flag in the ADC instruction. The next instruction INC-D increments the specified operand by 1 and accordingly affects all the flags, similar to the addition operation or add with the carry operation. For example, INC-AL increments 8-bit register AL by 1. Similarly, INC-AX increments the 16-bit register by 1. If this 16-bit register reaches its maximum value, increment by 1 initializes the AX back to 0. That means, the 0 flag will be set to 1 if the result of the increment AX operation is 0. The next important arithmetic instruction is DAA, which specifies decimal adjust for addition. The instruction is useful when the number is represented in BCD format and the expected result of the addition of 2 BCD numbers should also be in the BCD format. Take example of 2 decimal numbers 85 and 45. These numbers will be represented in the BCD format as 85 hex and 45 hex. As we know, in BCD formats, 4 bits are allocated to every digits. So, 4 bits in binary are needed to represent a digit. That means, the number 85 will be stored as 85 hex, the number 45 will be stored as 45 hex in the BCD format. When the addition of these numbers is performed using add instruction, the result is CA hex. When the DAA instruction is executed after the add instruction, it adjusts the results and brings the result in BCD format. The operation performed by the DAA is that it checks if the 4 least significant bits of the result is greater than 9 or the auxiliary bit is set, 6 is added to the first 4 least significant bits. Similarly, the 4 most significant bits of the result are checked to find if these bits are greater than 9 or the carry flag is set during the previous add or ADC operation. 6 is added to the most significant bits. As a result, when DAA instruction executes over the addition of 85 and 45, the result CAH is converted into 20 hexadecimal with a carry, which is in turn the result of the addition of 2 numbers 85 and 45 H in BCD format. Therefore, the DAA instruction is useful to make the BCD arithmetic efficient and saves a number of instructions otherwise required to achieve the same result. The next arithmetic operation or the instruction available in the 8086 microprocessor instruction set is AAA, which implies ASCII adjust for addition. The instruction is useful for adding two numbers when every digit of the number is expressed in ASCII format. For example, a number 2343 if stored in the ASCII format will require 4 bytes of storage, because every digit requires 1 byte and that byte represents the ASCII equivalent of that digit. Every byte contains the ASCII equivalent of 4 digits. In the example of a 4-digit number, the 4 bytes contain values 32 hex, 33 hex, 34 hex, 33 hex, which are nothing but the ASCII equivalents of 2343. The instruction operates and adjusts only on the register AL, and therefore, it is mandatory that the result must be brought in the register AL. Assume you have to add two digits 2 and 4 stored in registers AL and BL in ASCII format as 32 and 34. First an operation add AL comma BL is performed. The result 66H is stored in the AL. When AAA instruction is executed, it subtracts 60 hexadecimal from the AL. If the result is greater than 9, further a number 10 is subtracted from AL and AH is incremented by 1. Else the number AL contains the result of addition of two numbers. In the example, it contains 06 in AL and 00 in AH. If we add two numbers 36 hexadecimal and 37 hexadecimal, the register AL will contain 3 and register AH will contain 1 after the execution of the instruction add followed by AAA instruction, which stands for ASCII adjust for addition. So, what we have learned today are the various instructions of 8086, how they are executed, the instructions related to data transfer and arithmetic instructions like add were covered in detail. Thank you.